Thank you for that nice introduction. So as was mentioned, I hope to share with you today a little bit about some of the work that I'm doing. I sort of wear three hats, as was mentioned. But really what this is about is trying to advance prosthetic technologies to address a global need, okay? And I'm going to start off by asking you guys to reflect upon your day and think about how is it that you got here today? What made it possible for you to arrive here? And no doubt for most of you, probably all of you in the room, you used your 2 feet for at least part of your travels. And now think about, what if I didn't have the function of my feet and my legs? What would I do? What would I have done today to be able to come here to participate in this and all the other activities you have planned for the day? So walking and mobility are really important parts of our everyday lives. And now imagine you've lost the ability to use your legs. And so in the case of a major limb amputation, in this case the amputation of your legs, this is the case. So when you lose your leg, you lose the ability to stand, you lose the ability to walk. And if you don't have access to some kind of assistive device, then the predicament you're in is going to be quite difficult for you. You're probably not going to be able to work. You're probably not going to be able to be part of a community. You're probably not going to be able to support yourself. And that really speaks to the importance of mobility. And really as a basic right. As a basic right to have the ability to find food for yourself, to be able to make money to buy food, to have shelter, and to really have equal opportunities within a community. So it's not so dire if you lose your leg, because really if you're able to access a functional prosthesis, you can actually restore most of your mobility. So this is a very positive treatment that has been shown to have good outcomes overall, with most individuals with amputations who are fitted with a functional prosthesis are able to regain much of their physical function, including their mobility. Okay. So specifically today, and this is a lot of our research pertains to this level of amputation. It's called an above-knee amputation, or also a transfemoral amputation, because that's the bone that you're amputating through. And why is this level of amputation interesting? Well, it's actually one of the more challenging ones, because the higher the amputation level, the more of your limb you've lost, the more of those structures that are important towards physical function and mobility, including your joints, your muscles, parts of your nervous system. And so these all need to be replaced in some form or fashion by an artificial device. And in this case, we're showing what that might look like, which is basically a foot component, some kind of connecting components that sort of represent your bones, a knee joint that will typically articulate and allow normal movements around the knee, and then the socket or the interface, which is the part that attaches this whole prosthesis securely to your body, so it sort of acts as one system, and this is really important. And so when we are trying to advance prosthetic technology, or trying to provide functional prosthetic technology, really what we're trying to do is replace what has been lost in the anatomical limb. And so from the sort of left to right here, those aspects include essentially parts of the skeletal system, which is there for us to support us, to allow us to stand upright. It also includes joints, which allows articulation and movement around certain parts of our body. Second part of our system is the muscles, because the skeletal system on its own is just there to support us, but we also need to be able to control it and be able to move around. So really we have the muscles, which allow us to do that. They allow us to be stable. For example, I'm able to stand right now because my muscles are helping to support my joints. They also allow me to walk around, so they're able to generate dynamic movements. So that's the muscular system. But those muscles on their own, they're just the actuators. There has to be some kind of signals that go to these based on some information that the body has. So the nervous system has really two parts to it. One is the sensors, the receptors in our different parts of our body that allow us to take in information. For example, we have mechano and proprioceptors in our legs that tell us the position of our leg or the way that the leg might be loaded. And that then gives us information in terms of how, for example, we need to, what signals we need to give to the muscles to accomplish the task that we want to, or to stay stable, or to be able to produce a certain dynamic movement. And so these are now signals sort of come up from these receptors, get processed in our brain or in our nervous system, and then they go out to the muscles and tell the muscles really what the muscles need to be doing at that particular time, depending on what we're trying to do. And so this is just a really high-level overview of how our musculoskeletal systems and our nervous systems make it possible for us to achieve mobility. And some of these aspects of the systems is what we're trying to reproduce when we are trying to build prosthetic technology. And so I mentioned that above-knee amputees specifically have fairly good outcomes in terms of when they're provided with a functional prosthesis. So what is the problem really that we're trying to address? Well, there's sort of two aspects to it. The first part is that there's an estimated 10 million amputees around the world, and less than a quarter of these individuals actually have access to a functional prosthesis. So those pictures you saw of that child lying on the street, sitting on the street, that is the case in about 80% of the countries around the world, okay? And so that's a big problem. The second part of the problem, that even if we're able to provide a prosthesis, oftentimes the prosthesis may not provide the function to really restore mobility fully. And some of the limitations that we see within above-knee amputee populations include falling, and when a person has a fear of falling, they may not want to actually use the prosthesis and walk on it. We also see slower and less efficient walking. So imagine it took you twice as long to get from point A to B and you were twice as tired. Now you would be thinking twice about where you would actually want to be going, right? So these can be major limitations. In addition, there is the abnormal movements. So if biomechanically your prosthesis is not working well and you're having to compensate with your body by applying different types of movements, in the end, there can be long-term complications associated with that. We commonly see chronic back pain, for example, or joint problems later on in life in individuals where they're using a prosthesis in a way that's not biomechanically correct, and they essentially have abnormal loading and movement patterns. So these are all things that we want to improve. We want to improve the outcomes for individuals. First of all, we want to get more prosthesis on people in the first place, but we not only want to get a prosthesis on a person, we really want to put a prosthesis on a person that's really going to minimize some of these issues that they may have if they don't have a well-functioning prosthesis. All right, and so that takes me sort of to my three hats that I wear really to be able to do this. I need to, first of all, base this on science, on research, so we really need to understand, for example, biomechanically, what is happening between the interaction of the body and the prosthesis so that we can then use that information to design better functioning prosthesis. There's a lot of engineering. I'm an engineer by training that goes into this. So once we have some ideas about what the problems are, we need to come up with designs, and good enough designs that people can actually use them so that we can test them. And that's where the engineering comes in. So a lot of mechanical, electrical engineering into some of our work. And the final hat, as was mentioned, is Legworks, and that's a more recent hat that I've acquired. It's really taking the research that's born out of our lab and finding ways that we can actually translate it to and get it to the people that actually need it. And you may think that's fairly straightforward, but actually it can be quite a challenge, especially in academia where We are not the best salespeople, not the best business people. And so I've been fortunate enough with Legworks, which is a startup company, it's a social for-profit company, to be one of the co-founders with 3 other co-founders who are very business savvy and are able to help drive the business side of the translation of these technologies. And so before I move on to talking about some of these technologies that we are developing and trying to make impact with around the world, I'll talk a little bit about some of the methods, the research methods that we utilize in some of our work. All right, so one of the tools we rely very heavily on is our human movement laboratory. I don't know if you guys have seen any of these. You probably don't have them in your schools. These are fairly expensive. These are fairly fancy labs, and you may have seen them used in animation, similar technology where you put markers on the human body, and then you're able to track these within basically 3-dimensional space. And so in our biomechanical studies, we have specifically defined segment models. So we define the skeletal system in a certain way that allows us to determine what's happening at the different joints, both in terms of the movements. And we also have what you can see in the, probably not very well, but these force platforms in the ground, which allow us also to measure the forces on the body, which is very important, okay? So anytime we're trying to design a better prosthetic device, we not only want to make the movements more normal, but we also want to normalize the way that the person is loading their body, okay? Because we know, for example, when a person is wearing a very bad prosthesis, for example, if you're wearing a very uncomfortable shoe on one side, you'd probably favor putting more weight on the other. And that's the same case with individuals with amputations. So if they have a poor working prosthesis, they'll favor their intact limb. And that's okay for a little while, but after many years, they will run into problems where their joints will suffer. And so you can see here a little bit, that's kind of the lab there. These are some of the models we kind of get. And then we get these really funky graphs, and it takes a little bit of know-how how to interpret them. But they really give us very accurate and key information about how people are moving, how they're loading. And we can compare different designs, we can of different prostheses to understand how each of those is working. So that's all great, but we may have many dozens of designs that we are interested in testing, and oftentimes the people we want to test them on just don't have that much time to give us. And so we have to find other ways to try to understand how different prosthetic designs might work. And one way that we are doing this with is simulations or computational modeling. And so essentially what that is, we define sort of a human body system with a prosthesis in sort of a virtual space. This is digitally on a computer. We program this into a certain softwares that we use for this, and we're able to basically model the human body and the dynamics and the loading patterns of this system, which includes, as I mentioned, the body and the prosthesis. And these are really powerful tools because they allow us to test a lot of different iterations of designs without asking a person to walk hundreds of times within a human laboratory. It also allows us to test things without actually building them, because as you may know, building things is not, in the real world, is not as easy as perhaps doing it on a computer. Okay, so I'm not going to go through all the details of those models, but you can sort of see we define, let's say, the masses of the legs. That's important so that you can properly quantify the movements, the rotation, the forces of the muscles get incorporated in these models, the reactions with the ground, and all these other types of things. Okay. CAD modeling is another powerful tool, more on the engineering side again. So now once we know what we want to design, we want to be able to design it efficiently. We want to make sure whatever we design and eventually go to prototype, once we put it on a person, first of all, it's not going to break and injure the person. And second of all, we want to make sure that functionally it's going to, at least as an initial start, work well. And so we use a lot of computer-aided modeling. In this case, we're showing one of the tools, finite element analysis. This is a tool where you can virtually take the prosthesis and you can simulate the loading patterns on it that may occur, for example, during walking, and we can start to map out the stresses on the different components of the design. And for example, where you see on that on the right-hand side at the bottom there, the red areas, that would indicate stressed areas beyond the limit of the material. So we would then go back and we would take the part and we would strengthen it in those areas. In other areas where the blue is, that means there's not a lot of stress. We could perhaps take away some of the material to make the part a little bit lighter. And so we use these techniques to optimize the structural and also functional component features of the components. And even when we do that, sometimes things fail. You can see a failed component there. These are great tools, but they rely on certain assumptions and approximations. They don't always get at the truth right away, but they are extremely helpful and beneficial to speed up the design process. All right, so labs are great, wonderful, all these simulations are great, but then there's the real world. And so in the lab and in the simulations, we sort of get a sort of initial perspective how well these devices will work under, let's say, regular walking conditions. But really, when you get out in the real world, there's a lot of different types of mobility tasks you'll be doing, a lot of obstacles that you will be trying to overcome in your everyday mobility. And so this is why we're, for part of our work, trying to develop wearable systems with which we can instrument different prostheses, and we can actually start to understand what kind of mobility tasks are individuals doing within the community, but also how well are the prostheses working under those different conditions. And so in this case, we've got a number of sensors that are detecting the mechanics and the workings of the knee joint, as well as other sensors that are giving us the context of the mobility task, so sort of telling us how fast is the person walking, are they walking over up or down a hill, for example, okay? And we can start to sort of match this information together to understand under what conditions are the prostheses working well and where they are not. And then we can use this information to improve the design of our designs further. All right. So one area, so we worked on a lot of different projects. So I'm just going to highlight basically 3 of them here. One of them relates to prosthetic control. So we've done a lot of work in some very sort of sophisticated electromechanical robotic systems. And there's a lot of amazing work being done out there. You might have seen some of it, these robotic devices, actuated devices. While these devices are great, they are extremely expensive and basically don't really address that initial need that I've specified in terms of, even with current devices, most people really can't have access to them because of the high cost. So some of the most advanced prosthetic technologies out there can cost as much as a BMW. And most people can't afford a BMW, let alone BMW and prosthesis. So we're trying to develop mechanisms that are simple, cost-effective, that work well, but are going to be accessible to the greater populations. And so this is one of the projects that we have over the past decade, taken from conceptualization, and by that I mean developing a novel control mechanism, and for the last 4 years we've translated this technology to about 30 countries around the world. And it's a simple mechanism, okay? So it's very simple. I'm a mechanical engineer, and this is a mechanical device. And basically, what it does, it tries to mimic a little bit of what our muscles are doing. So as we're walking, and we put weight on our muscles contract to help stabilize our limb, okay? And that's one of the functions of the mechanism. It's a locking mechanism that locks itself as weight is placed on the limb, and then abruptly unlocks itself to allow the normal dynamics of swing phase. So the other part of the walking cycle, as you can see up there, which is when our leg is swinging, okay? And then we have another mechanism that's actually controlling the swinging motions there. We're calling that the variable cadence controller. so as I mentioned, we started this work. I guess it's now, based on those years there, over 10 years. But it's taken a number of iterations. As I mentioned, there's been the first 5 years, it was just iterations of designs and testing with individuals, and eventually going to production and starting to produce the technology, and then after that trying to commercialize it. Okay, and so here's a little video. Okay, so just really trying to show here the mechanics again. So you can see the person looks secure, they put the weight on the leg, they're able to do that fairly easily. At the same time, they're able to get a natural movement and flexion of the knee. And they're able to do this over a wide range of walking speeds. So I mentioned it's important to be able to do this, to be able to have mobility that's versatile. And one of the things is being able to walk slowly and being able to walk quickly. And this video, this treadmill video is there to show that. It's really showing that variable cadence controller, how it's able to adapt and allow the person to manage over these different speeds. And so this is a pretty good range of speeds. It's maybe not what you guys might be able to do. We've actually had this individual running. I'm going to show that video, but this is a good range of walking speeds. All right, and so in terms of the global impact piece, so through Legworks, what we're trying to do is we're really trying to build a model where we can provide the prosthetic knee to low-resourced countries, and we're doing that actually through our business model, which allows us to sell the technology in places such as Canada here, the United States is a big market, Australia, and Europe, and with having those operations, we're then able to work with different non-governmental organizations to bring the technologies to countries like Tanzania, which is one of our big projects. We're working NGO partners there to fit a large number of knees and studying how well these knees are working out in the field. Another place is Cambodia. We have, and another one is Ghana. So these are like three big projects we have going on, but these are all the countries currently where we're working. Okay. And this is a very short clip here just to show, I keep talking about how important it's that this device works in the community, not just on a treadmill. So here's some footage from some of our what we call clients, some of our users. A variety, we have the unilateral, one-sided amputation. You saw the bilateral, that's a very challenging case where now that individual is really dependent on the stability and the function of both of those knees and not able to compensate, as in the case of a unilateral amputee with their intact limb. All right. So I talked a little bit about how we're trying to replicate the function of the skeletal system and the muscles. Well, now I'm going to talk a little bit about some of the work we're trying to do to help bring back some of the lost parts of the nervous system. And so what is that? So you lose your limb, there's parts of the peripheral nervous system, the mechano, the proprioceptors. These are receptors that tell the body, for example, what kind of loading is placed on the limb, what position the limb is in. When you're an amputee and somebody sticks a artificial limb on you, you're not getting that information. And so part of what we're trying to do is figure out ways with which we can get some of that information back to the individual. So one of the research projects we're currently looking at is trying to basically apply sensors to the prosthesis that are able to measure certain aspects, for example, the position of the limb or the way it is loaded, and trying to communicate that information using haptics, so vibrations to the limb, to the individual. And we're really at a point where we're investigating how well can people actually utilize this information, what type of information we should be providing to them, how much information can we provide to them, because obviously there's so many different pieces of information in terms of the different positions, in terms of the different loading patterns, So really trying to understand the response, essentially the human response to some of this information. But you can envision essentially some time down the road where you might have a prosthesis that's instrumented with a bunch of sensors. This prosthesis is now able to determine exactly what's going on with it and around it, and it's able to effectively communicate that information to the user. Okay? And so we believe that'll not only improve, potentially be something that they can use on a daily basis to sort of help them better get around, but also a great, for example, training tool as they're starting to learn how to use the prosthesis, okay? So they can have a better sense of what the prosthesis is doing. So we're calling these the biofeedback systems. And some other work that we've done previously, again, it sort of falls under the realm of biofeedback, but this is a little bit more directed at sort of the training, trying to get the person and the prosthesis to function as one. Because you can design the best prosthesis, but if the individual is not properly using the prosthesis, the overall outcome is still not going to be optimal. So really a lot of what happens in prosthetic rehabilitation is trying to take a good prosthesis and trying to teach a person how to properly use it. I work at Holland-Bloorview Kids Rehab, which is a children's center, and sometimes it's not easy to keep children enticed in these sort of what can be mundane exercises of sort of balance and walking training. But we have investigated sort of more fun modalities. You guys may recall a number of years back the Wii Fit system, the balance board. So this was a great low-cost modality that allowed us to provide what we call physiotherapy in a fun way. And so basically what it is, as you may know, it's a balance board. You shift your weight around and that controls the different aspects of the game. This one is marble drop, so you're essentially tilting a table until a marble falls into a hole. And so this, as you may know, some of you played this? Yes? No? Yeah. So as you may know, it does take a little bit of fine motor control to do this. And what it also does for amputees, as I mentioned, they like to overuse their intact side, their non-amputated side, meaning they like to put more weight on it. This forces them to actually balance their weight equally over both of the limbs, which is very positive. And so we've done initial studies on this to show that kids who are playing these games are able to improve their balance, the way they distribute their weight. And we know that these sort of basic improvements in balance translate into better mobility down the road. But there's more research to be done on those aspects. So this is, I think I actually have a video of one of our participants. Okay, so you see the game there. This individual with a body amputation, and she's doing her best to improve her scores, so she's very motivated. She's been practicing and using this for about a month and continually gotten better. And we've seen improvements not only in her game scores, but also in her functional scores. So we measure things like her balance, her walking characteristics, and we saw improvements in those aspects. Okay. All right, well, so it's really a lot of, I think, information I shared with you in terms of some of the projects that we're trying to move forward, again, to address sort of globally the mobility needs out there in terms of cost-effective prosthetic technologies and also ways with which we can get people gait trained and using those prostheses properly. It's many years of work. You can see some of the members of our current lab, but there have been a lot of graduate and undergraduate students mostly from the University of Toronto who have been part of all of these projects. If you're very keen to learn more about some of this, we publish most of our work in peer-reviewed journals. They're really exciting papers to read. but if you are interested, that was where some of that information, detailed information, might be found. And I guess with that, I will open it up for questions. Thank you.